Hello friends, today we are going to introduce a procedure called Jacobi Iteration Method. Our objective is to solve a system of linear algebraic equations using Jacobi Iteration Method. So a system of linear algebraic equations in matrix form is given below. That is A times X equals B. A is the square matrix of dimension n by 1, and X is the solution vector which has the dimensions n by 1, and B is the right hand side vector which has the dimension n by 1. Here n is the number of rows or the number of columns of the square matrix A. In this case it is 5. The algorithm for the Jacobi iteration method is given below. That is, x of I, k plus 1 equals x of I, k plus r of I, k over a of I. Here I varies from 1 to n, where n represents the number of rows or columns of the square matrix, and r represents the residual. And r of I, k equals b of I minus sigma j equals 1 to n, a of I, j times x of j, k, and j varies from 1 to n. B represents the right hand side vector, and a represents the elements of the matrix uppercase A. And k here represents the iteration number. K varies from 1 to n iter, where n underscore iter represents the total number of iterations. In equation form, we have 4x1 minus x2 plus x4 equals 100, and so on. Now we need to calculate the residuals from these equations. The residual is given for the first equation as r1 equals 100 minus 4 times x1 plus x2 minus x4. If x1, x2, x4 are the true solutions for this set of equations, then the residual should be equal to 0. But since we are using an iterative scheme, we assume some initial values for x1, x2, x3 and so on. So the residuals are typically, they are not equal to 0. So they have some positive values. Our objective is to reduce the residual level to an acceptable limit. Let's assume the initial values for the x1, x2 and x3 as 0. So we can calculate the residuals using the previous equations given, since we know x1, x2, x3 and so on. So we calculate r1, 1 to be 100. Likewise, r2, 1 equals r3, 1 equals r4, 1 equals r5, 1 equals 100. So all the residuals are 100 in the first step. Also, ai, equals 4. ai, represents the diagonal element of the square matrix A. Here I varies from 1 to 5. Since the diagonal elements, they are identically equal to 0, in our case, we have ai, equals 4. For the second iteration, k equals 2, we have x1, 2 equals x1, 1 plus r1, 1 over a1, 1. We follow the Jacobi iteration method here, and we calculate x1 at the second step to be 25. Likewise, x2, x3, x4, x5 at the second steps are also 25. Then we need to calculate the residuals again. So r1, 2 equals 100 minus so on and so forth, and we calculate the residuals for the 5 equations at the second step. That is R1 equals 0, R2 equals 25, R3 equals 50, R4 equals 25, and R5 equals 0. We substitute the residuals and solve for the values of x at the next step. That is the third step. That is x1, 3 equals 25 in this case. And x2, 3 equals 31.25, and x3 at the third step is 37.5, and so on. Likewise, we can repeat the procedure until we get a very low value for the residuals, so that it is acceptable to our problem. So let's go back and look at the Matlab. So the procedure for the Jacobi Iteration Method is given here, and A is the square matrix we're talking about, and B is the right hand side vector. N represents the size of the square matrix, which is the number of columns or the number of rows. Let's assume the total number of iterations to be 20, and the Jacobi Iteration Method is given here. Once we follow this, let's see how we get the solutions on this. So the A matrix is over here and the B vector is here. The number of iterations we used are 19, and although we went for a maximum of 20, we don't need 20. We were able to solve the set of equations in just 19 iterations, one short of what we specified. So the first 3 rows, the values we already calculated, and the procedure is repeated. Matlab repeats the procedure using the loop specified, and finally we get the final converged solution. x1 equals 25, x2 equals 35.714285, x3 equals 42.857143, and so on. So when I try to use the Matlab built-in function to solve the this same set of equations, I get these values as x1, and these values, they are pretty close to what we obtained using the Jacobi Iteration Method. To summarize, in this video we presented an iterative procedure called Jacobi Iteration Method to solve a system of linear algebraic equations. So using this method we can solve a system of equations which has dimensions of which has n number of unknowns. For example, n can be up to 100 or more. In the next video we'll show how to solve a similar set of linear algebraic equations using other iterative methods. There are methods like Gauss-Seidel methods and successive over relaxation or SOR methods. Thanks for watching the video. Please let me know if you have any questions.